Hi guys, so we're from group 3 and today we're going to propose an experiment of experiment 5 which is called the bending moment. So our team members consist of a Tawante, Iman, Ilmam, Kwong and also me, Henry. So for the introduction, the structural equilibrium requires internal reaction force in a cross section to be represented by a resultant force and a resultant moment. And also the external force and internal reaction are balanced through the creation of shear force and also the bending moments. The experiment studies the dynamic relationship between external loads, internal reactions, and also the resulting bending moments. And also, lastly, the shear force and bending moments are essential in internal reactions, crucial to structural design. As for the objective is to measure the bending moment of material when subject to different loads at different distance. As for the scopes, we had two parts. The part one where we use different load, which is 0 Newton, 10 Newton, and 20 Newton. Meanwhile, the load hanger P1 was also placed 200 millimeter from fixed hanger P2 and hanger P3 was 300 millimeter from P2. As for the part 2, the load hanger of P1 was 200 millimeter from fixed hanger P2 as before, while P3 was 400 millimeter from P2. And also the range of load that we use is 0 Newton to 10 Newton. We have specific amount of loads that stated it's in the expected result. And also for we also did the distance P3 from point A are also 600 millimeter and 700 millimeter. So that's for our part 1 and part 2 scopes.
So next is the theory part. So in this experiment, the bending moment is considered. So bending is a formal process in which a force is applied to a structural element, causing it to bend at an angle. The bending moment refers to the reaction when an external force or moment is applied to the element that causes the element to be bent. So from this figure, we can see that the bending moment for beam A, which is MA, equals to RA times the A, which is the distance. So similar for bending moment for beam B. So MB equals to RB times B minus F times B minus X. So by equating these two moments, we can get MA is also similar to the bending moment we get for beam A. So we can show that this element is equilibrium and correct.
This is the experimental setup for this experiment. We have the beam labeled A, B, and C. A and B is part A and part B of the beam. C is hinge C. And then we have P1, P2, P3, which is the load hangers. And then we have RE and RB, which is the beam support at part A and B. And then we also have spring balance, loads, and bubble balance. Methodology part 1, where we use varied loads and fixed distance. We began by setting up the beam. The beam support RA was fixed at point A and the second beam support RB was placed 900 mm away from point A. Next, we positioned the load hangers. Load hanger P1 was set 200 mm away from the fixed hanger P2 and the load hanger P3 was set 300 mm away from P2. Before applying any load, we aligned parts A and B of the beam by adjusting the spring balance. This was done until the bubble in the balance level was centered, indicating that the beam was horizontally level. Step 4. With no load applied, we recorded the initial reading on the spring balance. This served as the zero load reference point in table 1. Then, we placed a 10 Newton load on the load hanger P1. The beam was realigned and a new spring balance reading was taken. The net force was calculated by subtracting the zero load value from this reading. After that, we removed the 10 Newton load from the P1 and repeated the process for load hanger P2 and then P3. For each, we recorded the balance reading and multiplied the net value by the fixed arm length of 150 mm to obtain the bending moment. Next, we increased the load at P1 to 20 Newton. Again, we realigned the beam and recorded the new spring balance reading. The net value was calculated similarly. Finally, the 20 Newton load was removed from P1 and the same procedure was repeated for P2 and P3. The net readings were multiplied by the fixed arm length to determine the corresponding bending moments. Next, for the methodology part 2, in this new setup, the beam support RA was again placed at the point A, and the second support RB was positioned 900 mm away from point A, similar to the previous arrangement. Then, we adjusted the position of the load hangers. Load hanger P1 was set to 100 mm from the fixed hanger P2, just like in the earlier configuration. However, load hanger P3 was moved to 400 mm away from the fixed hanger P2. This change was made to observe its effect on the beam's balance and resulting moment. Then, before any loads were applied, we leveled the beam once again by adjusting the spring balance until the bubble in the balance tool was centered. This ensured the beam started in perfectly horizontal position. Step 4. With no loads on the beam, we recorded the initial reading from the spring balance. The zero load reading was used as a baseline in table 2. Next, we placed 5 Newton of load on the fixed hanger P2. Additionally, 10 Newton loads were placed on both load hanger P1 and P3. The beam was realigned and the spring balance reading was recorded in table 2. Next, after removing all previous loads, we applied a new load combination, 6 Newton on P1, 12 Newton on P3. Again, we realigned the beam and recorded the spring balance value for table 2. Step 7. All loads were then removed again. This time, we applied 2 Newton on P1, 10 Newton on the fixed hanger P2, and 6 Newton on P3. These values were chosen to further explore how varying magnitudes and position of loads influence the beam. And then the beam was realigned for the last time and the spring balance reading was recorded. After this, all loads were removed from the system to prepare for data analysis. Lastly, to determine the reaction process RA and RB, we use the principle of moments. To find RA, we assume the moment about point B, MB, is 0. The equation used was load at P1 times 800 mm equals to RA times 900 mm. Solving this gave us the value of RA. And then to find RB, we assume the moment about point A, MA, is 0 using load at P3 times 100 mm equals to RB times 900 mm. After calculating RA and RB, we use the moment values and distance to plot a graph of bending moment versus distance.
So for the result for part 1, for P1, when the look is 0, the net force is 0, and when the look is 10, the net force is 24 minus 20, which is 4 Newton. When the look is 20, the balance reading is 28, and the net force is 28 minus 20, which is 8. So by using the same method, we calculate for P2 and P3 to get their net force. So for P1, the experimental bending moment for the look 10, we calculate by using the formula moment is equal to force times the distance. So for this case, the distance, which is the arm length and is fixed, which is 150 millimeters. And so the bending moment at C, we can calculate by using 4 Newton times the 150 millimeters to get the 600 Newton millimeter. So for theoretical bending moment, when moment at A is equal to 0, so for the 10 Newton times 100 millimeter minus the RB times 900 millimeter equal to 0, so we can get RB is equal to 1.111 Newton. So when the moment at B is equal to 0, so 10 Newton times 800 millimeter minus RA times 900 millimeter is equal to 0. So RA is equal to 8.889 Newton. So when the moment at C is, so we want to calculate the theoretical bending moment at C. So it's 1.11 Newton times the 600 millimeter. So we can get 666.67 Newton millimeter. So by using the same method, we can calculate for P1, P2, and P3, and for the load which is 10 and the load which is 20 to get the experimental bending moments and theoretical bending moment. So for the result in part 2, when the load P1, P2, P3 is equal to 0, the balance reading is 90 Newton and the net force is 0 Newton. So when P1, P3 is equal to 0 and P2 is equal to 5, the balance reading is 24 Newton and the net force is 24 Newton minus 90 Newton, which is the net force 5 Newton. And for P1, P3 is equal to 10 Newton and P2 is equal to 6 Newton. The balance reading is 32 Newton. So for the net force is 32 Newton minus 90 Newton, which is the 13 Newton. So when P1 is equal to 6, P2 is equal to 0, and P3 is equal to 12, the net force is 7 Newton, which is 26 minus 19. And for the P1 is equal to 2, P2 is equal to 10, and P3 is equal to 6, the net force is 15. So for the experimental bending moment, we calculate by using the formula. So moment is equal to the force times the distance. So the distance must perpendicular to the force. So for below example, we take when P1, P3 is equal to 10 Newton and P2 is equal to 5 Newton. So the net force is 32 minus 19, which is the 13 Newton. So the bending moment the bending moment at C is 13 Newton times 150 millimeter is equal to 1950 Newton millimeter. So this is 150 millimeter because this is the arm length and the arm length which is fixed. So for theoretical bending moment, when the moment at A is equal to 0, so we can get the resultant at B is equal to 10.5556 Newton. And when the moment at B is equal to 0, we can get the RA is equal to 14.44 Newton. So for this case, we must make sure the arrow. So when the arrow is point downward is positive, and when the arrow is point outward is negative. So that's why when the moment at A is equal to 0, the RB is negative. Is minus RB times 900 millimeter because for RB the arrow is point outwards. So for the theoretical value of bending moment is we at C is 14.444 Newton times with 300 millimeter minus the minus the 10 newtons times the 200 millimeters, so we can get the theoretical bending moment is 2333.32 newton millimeter. So we're using the same method to calculate the experimental bending moment and theoretical bending moment. So for the table, and we can get the experimental bending moment and theoretical bending moment. So from the table we can see the difference between the experimental bending moment and theoretical bending moment is not so big. So we can conclude that our experiment is quite reliable and is quite accuracy.
So next, for my part is discussion part A. As you can see, we have the graph for bending moment graph for P1, which is 10 Newton, and bending moment graph for P 20 Newton, and bending moment graph for P2 10 Newton, and P2 20 Newton. So for the P3, as you can see here, for 10 Newton and 20 Newton. Okay, the bending of the beam is larger when 10 Newton and 20 Newton of load was placed on the fixed hanger P2 compared to placing the same amount of load at load hanger P1 and P3. When load apply increases, the value of bending moment obtained will increase. Okay, for the explanation for discussion part A, based on the bending moment graph for P1, P2, and P3, with load of 10 Newton and 20 Newton, it can be seen that the theoretical values are slightly higher than the experimental values, but the overall shapes of the graph are similar. This shows that the experiment follow the expected trend of beam bending. When the load is placed at P2, the center of the beam, the bending moment is the highest compared to when the same load is placed at P1 or P3. This is because placing the load in the middle increase the distance from the supports, creating a larger moment. The graph also show that as the load increase from 10 Newton to 20 Newton, the bending moment increases proportionally. In conclusion, the bending moment depends on both the amount of load and its position on the beam, and the experimental result closely match the theoretical calculation with only small differences. Okay, next, this is the discussion part B, which we have. As you can see the graph here, and I will explain on the next slide. Okay, the graph above shows the four bending moment graph for different load setups on a beam. Each graph compares experimental results, which is the blue line, with theoretical values, the red line. In all cases, the graph have similar shapes, meaning the experiment work well and follow the expected bending behavior. Okay, first, when the load is in the center, which is P2, the bending moment is highest because it's far from the supports. Number two, when loads are on the sides, P1 or P3, the moment is lower or more spread out. Number three, as the load increases, the bending moment also increases. And lastly, the theoretical values are a bit higher than the experimental ones, but they follow the same trend. So, in conclusion, the bending moment depends on both how much forces is applied and where it is placed. The experimental results closely match what we expect based on theory.
So for the discussion for percentage error is calculated by using the formula experimental bending moment value minus theoretical bending moment values over the theoretical bending moment value, then times with 100%. So the table 3 is the percentage error for the part 1. So the table contains the experimental bending moment value and theoretical bending moment value and also the percentage error. So according to table 3, the percentage error recorded is consistently low at 0.1% for all position P1, P2, and P3 under the both 10 Newton and 20 Newton loads. So this indicates a high level of accuracy in the experiment result compared to the theoretical values. So for example, when a 10 Newton load was placed on hanger P1, the experimental bending moment was 600 Newton millimeter, while the theoretical value was 666.67 Newton millimeter. So this resulting in a minimum percentage error of 0.1%. Similar trends are observed for for P2 and P3. Okay, so moving on for the discussion of the percentage error for part 2. So from the table 4, we can see that the table also contains the experimental bending moment, theoretical bending moment, and also for the percentage error. So in table 4, the highest percentage error recorded is 0.25% when a 5 Newton load was placed on the fixed hanger P2. So other load configurations show slightly lower percentage error or below 0.25%. So for instance, when P1 and P3 were 10 Newton and P2 was 6 Newton, the experimental moment was 1950 Newton millimeter and the theoretical bending moment was 2333.33 Newton millimeter. So this resulting in a percentage error of 0.1643%. The lowest recorded error was 0.1118% for the configuration P1 is equal to 2 Newton, P2 is equal to 10 Newton, and P3 is equal to 6 Newton. So the small difference between the experimental and theoretical bending moment values can be attributed to several factors. So firstly, the load hanger may swing slightly due to external disturbance such as the wing or movement of the table. So this causes the load to be placed off center, affecting the moment arm. Secondly, the measuring instrument might be worn or damaged, such as faded scale marking on the spring balance. So this would reduce the reading's accuracy. So parallax error can also occur when the observer eyes is not perpendicular to the scale while reading the spring balance. So to improve the data accuracy, it's important to eliminate environmental disturbance such as turning off the fan during the experiment to prevent the hanger movement. So in addition, load hangers and fixed hangers should be stabilized properly before placing any weights on them. So lastly, the observer must ensure proper ice level alignment with the spring balance scale to minimize the parallax error. So, in conclusion, the objective of this experiment was to measure the bending moment of a beam when subject to various load at different distance. So, in order to observe how the load magnitude and position influence internal structural reactions, the experiment was divided into two parts, which is part 1, the load of 10 newtons and 20 newtons were applied at position P1, P2, and P3, while in the part 2, different load configuration were applied at varying distance. So the results show a clear correlation between increased load or distance and a higher bending moment. So the percentage error were calculated to compare the experimental value with theoretical ones. So in part 1, all positions recorded a consistent and low percentage error of zero point 0.1. In 0.1% indicating highly accurate measurement. So in part 2, the percentage error ranged from the 0.1118% to 0.25%, with the highest error occurring when the only P1 was loaded. So this small error confirmed that the experiment was conducted reliably and in accordance with theoretical expectation. However, some minor flaw was observed, such as the potential beam misalignment during load changes and slight inaccuracy due to the manual reading of the spring balance. So to improve further experiment, the use of digital sensor, more stable beam fixtures, vibration isolated surface, and repeated trial for each look setup is recommended. Overall, the experimenter effectively demonstrated the principle of bending moments and confirmed that both load magnitudes and distance from support significantly affect the internal reaction in a beam.
Okay, for the safety procedures, first, we need to wear proper shoes and lab coat to protect feet from falling awakes and to prevent clothes from getting caught during handling the apparatus. And the second one is secure the beam and stand firmly to prevent the beam tipping over, wake falling, or posing injury risk. Okay, next for number three, we need to use both hands when placing or removing weights to ensure better control and balance, preventing accidental drops or shift in the beam that could affect measurement. And lastly, use the spirit level to ensure beam is balanced and prevent incorrect data collection while avoiding sudden shift in the setup.
So this is some of the reference that we use in this experiment. So this is some of the reference that we use in this experiment. So that's all for our presentation. Thank you.